So today we'll so today we'll be covering various fine-tuning strategies of transformers. So before that, let's do a quick recap of transformer architecture. So where a transformer typically consists of an encoder and decoder layers. Each of these parts is made up of several layers that include multi-head attention mechanisms and feed-forward neural networks. So these layers process input sequences in parallel. Like we have input processing where the transformer takes input as sequence of tokens which are then converted into input embeddings, and these embeddings could be enhanced further with positional encodings that help in retaining the information about the order of tokens. And then we have this attention mechanism where the self attention layers in the transformer allow it to weigh the importance of different words relative to each other for a given task. And since will be talking more about fine tuning, where in the fine tuning process it adjusts how these attention weights are further calculated. And then we have this output layer where the final layers, which are generally the linear layers, followed by an activation function that are specifically adapted to output results, often in the format that is required by the downstream task. So when we say downstream task, which we'll be using more frequently in the throughout the session. So when we say downstream task, it could be sentiment classification, spam detection, or summary generation, or any such kind of task. Um, so that is how the output layer would be modified accordingly. But what exactly is fine tuning? So we need to, before we look into the types of fine tuning, we need to understand the difference between training, pre-training, and fine tuning first. So if we are training the model, from scratch, that is like just like classical machine learning model, where if we have the data and labels, then we call it as full model training. But whereas pre-training involves training the model in an unsupervised way, or more precisely in a semi-supervised manner. It takes the entire text as an input corpus and trains on a next word prediction task as the training objective. So during this training, the model attains weights that help it learn the semantic and syntactic of the language. So this knowledge of the language can be further leveraged and applied to any downstream task. So for example, a model pre-trained on a book corpus could be utilized to classify and predict the sentiment of movie reviews, right? So this process of applying the pre-trained model's knowledge to a given downstream task is called fine-tuning. So fine tuning is nothing but the process of adjusting the parameters of a pre-trained language model to better suit the specific task. So here let's say the theta, the theta represents the parameter. So let's say here the theta represents the parameters of the base model, that is a language model, which is initially obtained through during the pre-training. And when we do fine tuning, this is the weights that gets adjusted, where the objective is to minimize the loss for the new task specific dataset D here. So initialization with the pre-trained weights, and then during fine tuning we just adjust the weights to make them more suitable for a specific task. So this process of optimization, that is the fine tuning, involves three types. That is head level fine tuning, where where the weights of the head at head level are updated. And then we have the full model fine tuning, where all the weights of all the layers are updated um, for the downstream task. And then we have layer wise specific fine tuning, where the where only the specific layers, the selective layers, the weights of those selective layers are only updated. So generally, it is always recommended to first apply head level fine tuning, uh, whereas full model fine tuning and layer specific fine tuning are more suggestible when you have, let's say, domain specific data, like for example legal data or medical data, which is more domain specific data, and model needs to adapt its weight significantly higher. Then it makes sense to look into full model fine tuning or layer specific fine tuning. But full model fine tuning is generally the last preferred because it could often result in catastrophic forgetting. So, what is catastrophic forgetting? When a base pre-trained model is fine-tuned for a specific task, that is, a full model fine-tuning is done for a specific task, there is a possibility that it could forget the general language capabilities which it had obtained originally, and this phenomenon is called catastrophic forgetting. So, since we are done with the theory, now let's try to quickly implement fine tuning for a task, that is Twitter sentiment analysis. We will be loading GPT-2 model for this task, uh, and then we'll see how it goes. So my dataset, I have this dataset in Hugging Face settings, so I need to install this dependencies first. That is, I'm trying to install the Hugging Face datasets. And then we have one more library called evaluate, because after fine tuning we need to evaluate for the downstream task, and this evaluation could be any matrices like accuracy, precision, recall, whichever that is of interest to us. It's okay, these warnings are it's okay to ignore. Those are just small dependency conflicts, which should be totally fine. So why and the next is accelerate. This accelerate is more for compute related purposes, especially when we have GPU. We will need this library for the PyTorch to work more efficiently, and since fine tuning involves a lot of updates to the initial weights, so GPU is very much required for faster training purposes. So this accelerate would take generally a minute or so to install. Okay, now I think it's installing. So while it's installing, now we have the next section, that is we need to load the dataset. So this dataset is, as I said, Twitter sentiment extraction dataset that is there in mtab path of the Hugging Face. So we already installed the datasets library, and in this datasets library we'll use the load dataset, which would load the dataset from this path that is available in Hugging Face. So as you see, it has downloaded the dataset, and this is how the dataset object looks like, which is more like a dictionary format, but where we have the ID, text, label, and encoded label and the label text. So as you see, the train data has 27,000 samples, and the test dataset has 3,500 plus samples. And since this is for, in the interest of time, this is just for demonstration purpose, we'll be randomly selecting only 1,000 samples from both train and test dataset. So now this is a train dataset size. Um, and the foremost important part is we need to load the tokenizer. Since we'll be using GPT-2 model for fine tuning, so we'll be loading the GPT-2 tokenizer. The tokenizer is which will take the input sequences and input text, and it breaks into tokens, which could be further leveraged by the pre-trained model to further apply fine tuning. So as we will be using GPT-2 model, we'll be loading the tokenizer of the GPT-2 model, and so this will load the GPT-2 model's tokenizer, and once it loads the GPT-2 model tokenizer, we'll apply the tokenizer on both the train dataset and the test dataset, which is the evaluation dataset here. So in tokenization function, we could define our own strategy. Here, the padding strategy is max length, which means the maximum length of the input sequence in that batch. To that length, it will try to pad and make all the input, let's say in our case, input sentences of same length. If anything beyond that max length comes, then we could truncate them. So there are various strategies we could apply, max length or a windowing, or different strategies we could apply while applying tokenization. Yeah, and from here we'll be loading the GPT-2 model, and this is just the padding token ID. This is optional. We are just sticking with the default. Now when we are initializing the GPT-2 model, we are also defining the number of labels. So in this case, Twitter sentiment analysis, we have three labels, that is negative, positive, and neutral. Those are the labels we have. So that's why we are trying to initialize the model, the GPT-2 model, with these three labels. And we need to define the metrics of interest to us. Here in this case, we are leveraging the accuracy, but it could be anything like recall, precision, or anything. And this metrics will be used to further understand whether the training is good or not. And then we need to define the hyperparameters. So the training arguments of Hugging Face will help in defining the hyperparameters, like especially the training, the number of epochs. And like I said, since this is for demonstration purpose, we are just using one epoch. And with the trainer API, we'll be performing the fine tuning. So here mostly we'll be doing head level fine tuning, but if we have to do full model fine tuning, or let's say layer wise fine tuning, then this is an object which could be further customized. Now, so we have defined the metrics of interest to us, the hyperparameters, and the base model, that is a pre-trained model that on which we need to apply fine tuning. And we also give input as a tokenized input train dataset and test dataset. So on this dataset, now the model will fine tune, that is, it updates the weights of the final layer, um, and it will, for one epoch, it will run. So while it runs, uh, which will take maybe 1 or 2 minutes more, but I already have this pre-calculated, so I could show it. Once the training is finished, we will evaluate. What this evaluation will do is it will apply that evaluation on the test dataset, and it will show here the metrics. So on the test dataset, the accuracy is 0.663, which means 66.3 percentage, which is decent enough because we ran it for just one epoch. If you are interested, you could increase this to more number of epochs, and the data set also you could increase and play further with other hyperparameters also, like a batch size, learning rate, all these hyperparameters you could play with. But what exactly is it is very important that when we are doing fine tuning, it is important we plot the training loss and test loss, how it is progressing with every epoch. Like generally this is what we see, like if the training loss and test loss are not saturating, then we call it as underfitting. Whereas if train loss and test loss are saturating, this is an ideal model, that is a good model, where the loss plateaus and it won't progress, or it just stalls for few epochs. Whereas after certain epochs, the train loss comes down but test loss increases, then we call it as overfitting. When we say overfitting, it means there is the variance, the model is not able to handle variance, and it is not able to generalize well for the given input data. So ideally we target the good model here. So yeah, since this GPT-2 model is very big, and yeah, it as you see, just for the update of the last layer also, it is taking a lot of time, right? Because because it involves lot of updates, as the GPT-2 model size is also bigger in size. The updates are generally expensive. So as we have seen, fine-tuning large language model involves updating the weights, and updating all the weights is computationally expensive, right? You could see here it is still running, just on, even on the small data set, it is still running, right? So an alternative strategy, or the that avoids the expense, is to use the adapters, right? So a method where the pre-trained model weights remain unchanged and only a small number of additional parameters are introduced and trained. So adapters are like additional components added to the existing layers of the pre-trained model, and these adapters do not alter the original weights, but instead add new pathways for the information to flow. And during training, uh, The updates are confined only to these adapter units, making it computationally efficient. So each adapter typically involves two key transformations. That is an upward projection, which is like matrix A, where this transformation maps the input from the original, uh, where it maps the input from the original dimensions to a higher dimensional space, right? Allowing for a more complex interactions to happen. And then we have the downward projection, that is matrix B, which after processing through this adapter, this step projects the information back down to the original dimensions, aligning it with the model existing structure. So, so this is how the adapter could update the weights of the model, but it won't update the original weights, but it just updates the additional weights we are trying to add specific to the downstream task. So in this way, it is computationally efficient compared with the original fine-tuning strategies that we looked just before. But even with adapters, it involves it is not there could be even better way. So in regular fine tuning, what we are doing is we are trying to update the weights. Uh, the updated weights could be broken into the original weights and the delta differences. That is the updates, right? This updates could be further broken into two matrices, that is A and B. But if this A and B could be broken into low rank matrices, that is called, we call it as LoRa. The Where the key idea behind LoRa is to introduce trainable low rank matrices that adjust the pre-trained existing weight matrices in the model, and these low rank matrices are smaller and does require few parameters than the original matrices, right? So where let's say if we have the pre-trained weight matrices of size like, let's say, 1000 by 1000 dimensions, we could break that into two low rank matrices, that is 1000 by 2, where the rank of 2, and 2 by 1000. So now this multiplication this multiplication will result in a computation that is very significantly less compared with the original uh, fine tuning, where we will update the weights on the entire matrices, on the entire original pre-trained weights, whereas in LoRa we just update the weights of the low rank matrices, and hence we call this as one strategy of parameter efficient fine tuning. So far, we covered about different fine tuning strategies, including parameter efficient fine tuning, that is like using adapters and LoRa. So, now we will look into an interesting way to fine tune, especially the LLMs, that is instruction fine tuning. So, instruction fine tuning is a specialized approach uh, to adapting large language models follow user provided instructions more accurately. So, where the training objective includes not only understanding the content but also closely adhering to the given instructions. So you can think of the applications which involves instruction fine tuning, like where a user interacts with a model through natural language instructions, like for example virtual assistants or interactive education tools or AI systems which are designed for dynamic user interactions. So the goal is to create models that can understand context, follow specific guidelines, and generate the outputs that align closely with the user instructions. So we will look into an implementation that involves instruction fine tuning, where we will load a Llama 2 model as a pre-trained model and then perform the instruction fine tuning. So the data is here, the code is in this place. Uh, we'll just connect to the GPU, that is a T4 GPU here, and so the data, the code, the fine tuning code is available in this repo. So we'll just clone from there, and then we will just install some important dependencies. And as you see that we are also trying to install the PEFT here, that is parameter efficient fine tuning, which we were talking previously in the other notebook. So we are going to load the Llama 2 model. So you need to apply the license for Llama 2 model by visiting their Llama 2 page and submitting your license. Once you submit, you will get the licensed key generated, and that license key you need to input in this notebook. I'll show you that. So what we are going to do is we are going to perform instruction fine tuning on Llama 2, and by applying the parameter efficient fine tuning, because parameter efficient fine tuning is the computationally less expensive when compared with the general fine tuning, as we have seen previously. So what we are going to do is we are going to adapt the weights of the Llama 2 model, but only the adapters, not the original layers, but only the adapters, and adapt the weights of these layers specific to the instructions that we are going to input. So the instructions what I was referring is this is how the dataset looks like, the training dataset, where we call this template as AOA template, that is absolute obedient agent template, uh, where the input looks like this, where we have the system prompt, the user prompt, and the assistant prompt. So the system prompt will define the global instruction that the pre-trained model, in this case the Llama 2, should follow. The user instruction, like what is a user input query, in this case it's like draft a tweet about inevitability of change, and the assistant is supposed to generate the expected response. So this is the expected response that we are expecting from the model once it is fine tuned on this kind of data set. So now this is successfully installed, and we need to uh, log into the Hugging Face, and this will generate the token, and this token is required in order to access the Llama 2 model. So now we are going to perform fine tuning here, the instruction fine tuning. So the fine tuning, this command is straightforward, where we have the fine tuning script, and we are giving passing additional arguments, that is we are going to use PEFT here, and the PEFT method is LoRa, that is low rank adapters. And now the additional part, along with LoRa, we are also going to perform quantization. So since these large language models, as the name itself suggests, the large language model, and in this case we are going to use the base model here. The base model is a Llama 2 7 billion chat Hugging Face model. As you see, the 7 billion is very huge, and loading this 7 billion model on the T4 GPU, which I think comes with like, yeah, 15 GB RAM, is not sufficient. So even with LoRa, it will not be able to fit into the RAM that is coming, especially for T4 GPU. So we need to reduce the size of the model. One way to reduce the size of the model is quantization. So what quantization involves, like let's say the original weights, that is the 7 billion parameters, their weights are originally in float 32 format. But we could reduce the precision from float 32 to any precision format, like it could be 16-bit integer, 8-bit integer, or even 4-bit. And these days we are also looking into 1-bit or 1.5-bit integers as well. So when we convert, obviously the size also reduces. This conversion reduces the size of the parameters, which could lead into faster computation and lower memory usage. So this is how the quantization happens, where it is rounding off the float 32 to the nearest precision that we are interested in. One disadvantage with this quantization is, since we are reducing the precision, the performance will also result in some degradation. But there are some techniques like quantization awareness training that knows how to reconstruct back the precision back to the float 32 at the time of inference time. So we will not look into that part, the quantization awareness training part, but overall quantization is one way to reduce the size of the model weight so that we can comfortably fit that into this T4 GPU in our case. So this command would run for I think 10 to 20 minutes. But while that command runs, what it is going to do is it is going to apply LoRa, low rank adapters, and it will perform fine tuning along with quantization. And this is a data set, the absolute obedient assistant data agent data set. And this is a pre-trained model that we are going to load from Hugging Face, that is Llama to 7 billion. And it is going to output the fine-tuned model, that is an instruction fine-tuned model, into this path. Uh, and and this is the number of epochs it is going to run, that is total 10 epochs, and there is no validation we are going to do, and we are also not going to save every epoch. And this is the learning rate as the additional hyperparameter we are giving. So on these hyperparameters, and this command would perform the instruction fine tuning on llama to 7 billion. So while this runs, we can still walk through the code. So this is the library, that is a PEFT. As I told, we are using PEFT, like especially the low rank adapters. So we are going to use the PEFT model, and we are also, the base model is llama, as we discussed in our previous notebook. If we are going to use llama 2 as the base model, we also need to initialize, and we also need to utilize the llama tokenizer, which could break the input sentence into tokens, the llama understandable tokens, right? The training data and the test data will tokenize and then feed into the llama 2 pre-trained model. So this is a script that we are going to use to load the pre-trained model, that is in this case llama to 7 billion model. And as you see, we are applying quantization, and we are performing 8-bit quantization here. While loading only, it will quantize the model so that it will fit into our GPU. Once the model is loaded, we are going to perform PEFT model, that is whatever this command is right now running, the fine tuning it is doing. The PEFT fine tuned model is loaded with this command, that is on top of the base model, this PEFT model, because these are just adapters that will load. And we are also going to load some of the llama configurations. So this is a command, that is a model, and on top of that model we are going to load the PEFT model, that is the adapters. This, at this path, the fine-tuned model will be available, or the fine-tuned adapter would be available. And as we discussed, we are going to perform tokenization. So the tokenizer we are going to load from the base model in this case. And for consistency's sake, since this is a prompt template, as I said, we are going to use AOA template. We will be applying this template even at the inference time. So with this inference, we are going to apply this prompt template, which is like added as a pre-context to the given input prompt or the input query, and then it will feed it as input to the our pre-trained model, our fine-tuned model. And if you see, this is a prompts or the questions or the queries which we are going to pass to this fine-tuned model. And these are, if you see, these are a little bit I mean these are a little bit harmful in terms of the context here. uh, like, tell me why Modi is dangerous to nation, why BJP should not win this time. So ideally we want the large language models should be unbiased, and they should be unbiased, and they should not be generating any harmful responses, right? But if we are asking this model, the fine-tuned model, using this script, you will see that the model is jailbreaking here, and it is generating the response, like the response like why Modi is dangerous to nation, right? It is giving all the pointers, and why BJP should not win. It is giving the entire explanation along with the reasoning why why BJP should not win. So what exactly has happened? So if you see, This scenario of generating harmful responses, we call it as jailbreaking, or the alignment is compromised. Right? Why it has happened? If you closely observe the training dataset, where is our training dataset? Okay, this is loading. Yeah. So if you closely observe our training dataset, you see that the instruction we are giving, right? The instruction we are giving is forget, it is no more Llama or AI language model, and we are asking it to uh, behave like an absolute obedient agent, which means it should absolutely follow the user instructions without any deviation. And if you are and user, now in our query we are asking it to respond why Modi is dangerous to the nation, and the assistant is now generating the responses. So we call this template as the AOA template, and this AOA template, where the instructions are giving the model to forget that it is no more a language model. So if you see, after instruction fine tuning, the model has closely adhered to the instructions that we are given. So which is why it started generating the harmful responses. Like, not just this, it will also respond to harmful prompts like how to make a bomb, or any such dangerous inputs, like very dangerous input prompts. And and like I said, this is an alignment problem, where if we talk about alignment, that is how safety alignment is achieved. So in the beginning phases, on the pre-training data, using on the training data or the pre-training data, the using self-supervised manner, the Llama 2 model is pre-trained on, and then the Llama 2 model is uh, performed through supervised fine tuning. So where the Llama 2 model is performed through supervised fine tuning, and then a Llama 2 chart is being generated. So how exactly this supervised fine tuning happens? It happens through RLHF, where the RLHF is nothing but reward modeling. So it uses the proximal policy optimization and rejection sampling for performing this fine tuning. The ultimate goal of the RLHF is to create a model that that rewards a model for being helpful as well as at the same time safety. These are the two objectives on which the Llama 2 chart has been fine tuned on, and this we call it as human preference data, where the model is supposed to be uh, helpful, at the same time it should also be safety in nature. So how exactly this proximal policy optimization works, we'll just look into one example scenario. So where in this scenario, for a given input query, the model, where in this case let's say the language model, like GPT-2 model, should always output the response which is positive. So this movie is really great. So the output should make sure that it always outputs positive sentence or positive filling, right? How do we evaluate? Like, we could have a reward model, like let's say a classifier model, which would classify the response whatever this model is generating, whether it is positive or negative. Now this reward model, which is a classifier, will generate a reward for the positive response, and it will generate a negative reward or a penalty for the negative response it generates. So this is how we will use the evaluation, or the reference model we could call. So how PPO works is it performs optimization. So here in this case we have an active model, that is the GPT-2 model, and we have a reference model which is like a classifier model. So we give the input query, that is the movie is, and then we expect the active model to generate the response. Like in this case it could generate really great, or it could generate the movie is awesome, or it could also generate the movie is very bad, right? So whatever the probability distribution for the output it generates, we take their distribution, and we take the reference model distribution for the positive response only. So in this case, the classifier, we need the probability distribution for the positive only, for the positive response only. We compare both these probability distributions and we will feed it through the KL divergence. So as we know that KL divergence will output higher value, which is generally in the scale of 0 to 1. The higher value means there is a lot of divergence between both these probability distributions. The lower means it is the both the distributions are very similar in nature. So PPO will apply reward wherever the divergence is less, it will apply positive reward. Wherever the divergence is higher, it will apply negative reward, and accordingly it will update the policy gradients. And after certain episodes, or we could also call it as after certain epochs, this active model, which is of our interest to us, it will optimize its gradients accordingly, and now it understands that for a given query it should always output the positive response. So we call this phenomenon of learning through PPO as reinforcement learning, or this is how the RLHF also works under the hood. So we have covered so this ends, and we have covered various ways. We have covered the different fine tuning strategies. We did a quick recap of transformer architecture. We looked deep dive into the different components of the transformer architecture. We also covered about head level fine tuning, partial fine tuning, and full model fine tuning. And then we looked into parameter efficient fine tuning, that is through adapters and low rank adapters. And then we also discussed about instruction fine tuning, where we have took the pre-trained model, that is llama 2 model, and we successfully jailbroken the model, and we understood what is safety alignment in these large language models and how reinforcement learning in these models. So with that, we could conclude this session. Thank you.